Hi there, and welcome to a Scratch tutorial. First of all, thank you to everyone who responded to the poll. Since I started this series, I've gotten a lot of requests to add enemies and weapons to the engines, and the response on the poll I posted overwhelmingly supported it. So finally, in this video, we will be adding basic enemies and weapons to our engine. By the end of the last video, we added physics and collisions for objects. In this video, we will use those object physics to add basic enemy movement, along with a player weapon. Before we get started, it's worth mentioning that while the focus of this episode will be enemies and weapons, the code can be used for non-player characters and tools. For example, the scripts for checking if an enemy is hit by a projectile can easily be changed to allow the player to push a button. This will make it a versatile and useful tool to have in the engine. In case you haven't been following this tutorial series, I've made the code up to this point available on Scratch, and you can find it at the link in the description. Now, let's get coding. To start, let's make a copy of this project. The code is getting pretty expansive, and it's good to have a copy in case it stops working at any point. Now we can begin working on enemy movement. As usual, we'll first make a new custom block. We currently have custom blocks for adding different types of objects, so it makes sense to have one for adding enemies. Let's give this add enemy custom block inputs for X, Y, and Z position, width and height, and health. We can duplicate the code from the add object with physics custom block to start. Here, the object type variable should be set to enemy. We'll set the initial speed to 0, then use the width and height inputs to initialize the object dimensions. For the final input, health, we need to make a new variable. Let's call it object health and make it for this sprite only. Now we can set the variable to the health input. And with that, we are done with this script. Down in our frame script, we'll use an if block to check if the object type is an enemy. If it is, we'll run some special physics code. First, we'll set the friction to 0. While this friction is great for most objects, characters need a friction that's more like the type that the player uses. We'll also set the bounce input to 0.3 so that characters won't bounce at all. Next, we'll make a new custom block to actually move the enemies. We'll call it move toward and give it inputs for X and Z positions, acceleration, and drag. Normally, we would include Y position, but Y is height off the ground, and we want enemies to move along the ground toward a point regardless of height. Before we add code to the new custom block, let's add the custom block itself to the frame script. For now, we'll use camera X and Z to move the enemy toward the camera, but we can put in any position to have the character move toward any point. Finally, we can do an acceleration of 2 and a drag of 0.9. With that out of the way, we can start adding code to this custom block. But how exactly can we move a character toward a point? To find the answer, let's start by drawing a right triangle between the character and the target. The longest side, the hypotenuse, is the distance between these 2 points, so let's label it D. We can call the triangle's legs dx and dz. The length of dx is equal to target x minus object x, and the length of dz is equal to target z minus object z. Now let's set up another right triangle, smaller but in the same shape as the first. This one represents how much we want the character to move. The custom block's acceleration input tells us how fast we want the character to accelerate, so let's label the hypotenuse A for acceleration. The 2 legs of the triangle, which we can call AX and AZ, are the values that we want to find. They will tell us the speeds we need on the X and Z axes to move toward the point. Using geometry, we know that AX over DX equals A over D. Multiplying both sides by dx gives us ax equals a times dx over d. If we substitute in our variables, we get x acceleration equals acceleration times target x minus object x over distance. The same goes for z values. Now we can put these equations in our code. You may have noticed that these equations use the distance between the character and the target, but we don't actually have that value yet. To get it, we'll make a new variable for this sprite only and call it distance. Let's use the Pythagorean theorem on the x and z axes to get the horizontal distance. Now we can code the rest of the equations. You'll notice that we are not changing the object's position, but instead changing its speed. This is because the move toward block only changes the speed to essentially push the character in the right direction, while the object physics block is the one that actually moves the object and checks for collisions. Finally, we can use the drag variable to slow the character down, keeping it from going too fast. Now that this custom block is done, we can test our character code. But wait, first we need an enemy costume. The skeleton costume will work for now. Let's just make sure it's centered in the costume editor. Here we can see that the costume has a width of 116 pixels and a height of 179 pixels. We'll use these values for the object's width and height. Back in the code, we can use the Add Enemy custom block to add a skeleton enemy to the world and test our scripts. We'll start it with an x of 0, a y of 100, and a z of 600. This will put the skeleton directly in front of us, slightly above the ground, and a short distance away. We'll use the width and height of the skeleton costume for the width and height inputs. Finally, let's give it a health of 10. Now we can test it. And there it is! If everything has been coded correctly, you should have a skeleton that follows you around the world. Now, you may have noticed that when the skeleton catches up to you, it disappears. This is because it is getting way too close, walking right through the player. We can fix this by adding a minimum distance input to the Move Toward custom block. By adding an if block, we will allow the character to move only if the distance between the character and the target is greater than the minimum distance. Back in the frame script, let's set the minimum distance to 200. Perfect! As predicted, the skeleton stops a short distance away from the player. Now that we have a basic enemy, we really should give the player the ability to damage an enemy. One of the easiest ways to do this is with a Hitscan weapon. The idea of Hitscan is that we do not simulate moving projectiles. Instead, we check to see if there is a straight line between the player and the enemy, then instantly deal damage. To put this in our engine, we'll make a new sprite and call it HitCheck. For a costume, we'll put a small circle in the center of the screen. Let's make a new variable and call it check4hit and make it available for all sprites. This variable will tell the objects when they need to check for a hit scan. When the green flag is clicked, we'll wait until the mouse is clicked, then set check4hit to 1. Then we'll wait for the mouse to be released before repeating the loop. Back in the object sprite, we'll make a new custom block and call it HitCheck. We want every clone to run this script after being positioned on the screen, so we'll put it after the 3D projection block. To start on the HitCheck script, we'll use an if block to make sure the check for hit variable is 1, which indicates that the Hitscan is active. We'll next check if the object is touching the HitCheck sprite. If both of these conditions are met, we can stop the HitCheck by setting the check for hit variable to 0. If the object is an enemy, we should also reduce health. With an initial health of 10 and each hit taking away 4 health points, it will take 3 hits to bring the health down to 0. Finally, if an enemy's health is no longer above 0, we can delete the enemy. If you're confused about why this script will work, we have to remember that clones run broadcast scripts in layer order. Because of this, closer objects will run the hit check first. This prevents us from hitting enemies through walls. Now let's test our scripts. And there we are! 3 clicks caused the clone to delete itself. However, there is one small bug in our scripts. Everything works when the HitCheck sprite is touching an object clone. However, if the HitCheck sprite is not touching an object clone, the check for hit variable stays at 1, and the engine continues to check for a hit until the HitCheck sprite touches an object clone. To fix this, we need to set the check for hit variable to 0 after all the object clones have run their HitCheck scripts. Remember how broadcast scripts are run in layer order? Since the horizon sprite is always at the back, its frame script will always run last. If we set the check for hit variable to 0 here, it will always reset the variable after all object clones have run their HitCheck scripts. Now when we test it, the bug is fixed and the Hitscan script works. For your project, if you don't want a big circle graphic in the middle of the screen, you can use the ghost effect to hide it. This will keep it hidden, while at the same time object clones will still detect if they're touching it. For now though, I'm going to keep it visible to make it easier to test. Now, a big circle is great for testing the Hitscan, but in practice it should usually be a bit smaller. That's a bit better, but now it's a lot harder to aim. This seems like a great time to add mouse turning, which will make aiming a lot easier. Let's start with horizontal turning. Instead of changing the camera Y direction when a key is pressed, we'll change it by the mouse X position times some number. This will allow us to turn quickly or slowly depending on where the mouse is. Here we'll use 0.02, but you can play around with different numbers to see what works best for your game. After a quick test, we can see that it works. Next, we need to add vertical turning. Since there are limits to how high and low we can look, we can use the Set Camera X Direction block. If the highest we can look is 50 degrees, it may be different in your engine, then a mouse Y position of 180 at the top of the screen should produce an angle of 50. We can do this by setting camera X direction to mouse Y position times 50 divided by 180. When we test it, we can turn with the mouse and it is a lot easier to aim. At this point, we've added all of the foundational code for this episode to the engine. The rest of this video will be dedicated to taking what we have and adding weapon graphics and effects that are common to games with first-person weapons. If your game doesn't use a weapon graphic, feel free to skip the rest of this video since it won't be necessary in future videos. For a weapon, we can upload a new sprite. You can find this sprite at the link in the description. This sprite comes with 2 costumes. The first is the Plasma Blaster, and the second is the muzzle flash, which appears for a second every time the weapon is fired. Before we go any further, let's talk about Scratch's policies on weapons. Strictly speaking, Scratch hasn't officially released guidelines on what they will or will not allow, but there is a general rule of thumb you can follow. If you want to share a project with a weapon on Scratch, it should not look like a real-life weapon or make realistic sounds. There should absolutely be no blood. This project is acceptable because the weapon does not look like a real-life weapon and the enemies are not scary or gory. If you can work within these rules, great, but if you can't, you still have some options. If your work is too violent or scary for Scratch, you can share your Scratch projects on other sites. Game Jolt, for example, is a popular place for Scratchers to share their work. For instance, D7 Studios on Game Jolt is a whole community of Scratch developers who specialize in clone-based 3D and similar styles. Getting back to our engine, let's add some code to this weapon sprite. When the green flag is clicked, we'll position the sprite in the center of the screen and change to the Plasma Blaster costume. When I start as a clone, switch to the Flash costume, then position at X 80 and Y -80. This will put the Flash costume right at the end of the blaster. This also means that every clone we make of this sprite will become a Flash. Next, we can use a repeat loop along with the effect block to fade the Flash out over 10 frames. The ghost effect combined with a reverse fisheye effect works nicely for this. Finally, we'll delete the Flash clone after it has faded out. Next, we need the code to make a clone of this sprite every time the weapon is fired. Let's go into the HitCheck sprite, copy its script into the weapon sprite, and delete the original copy from our HitCheck sprite. Now we can go back to the weapon sprite and combine the new script with our existing green flag script. When the mouse is clicked, we'll have the script create a new Flash clone. For a final effect, we can have the Flash costume point in a random direction when it appears. Now we can test it. That is looking pretty good. This is a good time to add some other elements common in games with first-person weapons. The most common one is the reticle or crosshairs. Many games use the reticle to tell players if they have hit an enemy by flashing some sort of indicator. Reticles come in all shapes and sizes, but we'll start with a pretty ordinary one. First, we'll select the paint option to draw a new sprite and call it Reticle. Let's start by making a rectangle and bringing in the corners on one side. We'll center it, then use Shift plus left arrow to move it out from the center. We can hold down the Alt key and click the shape to duplicate it. Next, we'll center the new copy, turn it around, and move it out the same number of spaces to the right. We'll then duplicate both shapes and rotate them, holding down Shift to snap to angles. Now we can add a circle outline and center it on the costume. Using the eraser tool, let's take out segments near the purple boxes. Finally, we'll thicken up the line, shrink it down a bit, and recolor the purple boxes. Now our reticle costume is done. We can duplicate this costume to make the hit indicator costume. I'm thinking a red ring around the inside of the reticle would work well, so let's duplicate the ring pieces by holding the Alt key and clicking, color the new red pieces, and shrink them down to just touch the inner edge of the reticle. We'll just remove the non-red pieces, and with that, our hit indicator costume is complete. Now we have our two reticle costumes, but how do we code them? We'll start by positioning the sprite in the center of the screen and switching to the reticle costume. Let's use the ghost effect at 50% to make it semi-transparent. For the hit indicator costume, we can make the code similar to the weapon sprite and have the hit indicator appear as a clone for only a second. To start, we'll go over to the object sprite and scroll down to the hit check custom block definition. When an enemy is hit, we'll make a clone of the Reticle sprite. Meanwhile, back in the Reticle sprite, we can add a when I start as clone block. We'll have every clone change to the hit costume, remove the ghost effect, then fade out over several frames. Finally, we'll delete the clone. When we test the script, it works, giving us a nice indicator when we hit an enemy. Now, this reticle seems a bit big to me, so I'm going to make it a bit smaller. Of course, the best size and shape for your reticle will depend on both the weapon and the game, so do whatever you think works best. I don't know about you, but I feel like this weapon should make some noise. The Scratch sound library has a sound effect called Pew that could work here. Let's add it to the weapon sprite. When the weapon is fired, we'll play the sound effect. We can also randomize the pitch to give it a bit more variety. The graphics are looking better, but adding recoil to the weapon could really improve the feel of it. To get more realistic recoil, we can code some springs. The idea behind using a spring is that instead of fixing the weapon at a point, we will have the spring push and pull the object towards a point. The farther away the weapon is from the resting position, the more the spring will push it. This gives us a nice effect where the weapon bounces around before settling back into place. To code this, we'll make a new custom block called Springs and give it inputs for strength, drag, and a target X position. Eventually, we'll add springs for Y position, direction, and size, but X position is a good place to start. The strength input will determine how hard the springs pull on the weapon, and the drag input will control how fast the movement slows down. The target X position is the point the spring is pulled towards. We'll start by putting the custom block in a forever loop when the green flag is clicked. Let's give the spring a strength of 0.1 and a drag of 0.9. This will give us a weak spring that takes a while to slow down. We'll have the weapon follow the mouse by setting the spring's target X to the mouse X. To code the custom block itself, we need to create a new variable called spring X speed, making it for this sprite only. This variable tells us how fast the weapon is moving horizontally. We'll change the speed by the spring strength times the horizontal distance between the target and the weapon. This will push the weapon towards the target position. Next, we'll change the weapon's X position by the X speed. If we test the script here, the weapon oscillates back and forth without slowing down. In order to slow down, we need to add in the drag. We'll do this by setting the X speed to the drag times the X speed. If the drag is between 0 and 1, it will always decrease the speed. Now let's test it. And there we are. The sprite wobbles back and forth before settling into the target position. But wait, we're not done yet. We still need to add springs for Y position, direction, and size. We first need to add new target inputs to the springs custom block. We can fill these inputs with mouse Y for Y, 90 for direction, and 100 for size. Next, we need 3 new variables, all for this sprite only. Spring Y speed, spring direction speed, and spring size speed. Luckily, we can duplicate most of our existing code and swap out X position and speed for Y, direction, and size. We'll start with the change variable block. We need 4 of them in total, 1 for each attribute. Now we can put in corresponding blocks for Y, direction, and size. We'll repeat the process for the drag code with the set variable block. Finally, we'll update the position, direction, and size. When we test this script, we get full sprite movement. Now, the code works, but I think it would look better if we made the spring stronger and increased the drag. Let's try a strength of 0.4 and a drag of 0.7. That is already looking better. However, something is wrong here. Scratch says the sprite size is 86, but we told it to be 100. It turns out that this costume is so big, Scratch won't let its size be 100, and instead the maximum size is 86. To fix this, we need a new costume. Let's call it Sizer. We'll put a medium-sized circle in the middle of it. This costume can be as small as 3 or as large as 367, which gives us a good range. Back in the code, we'll switch to this costume before we run the custom block, then switch back to the blaster costume after. This means that the size range will apply to the Sizer costume, but we'll still see the blaster costume. When we test it, we can see that the size settles to 100, which is what it should be. Now, the springs are good, but the weapon really shouldn't follow the mouse around this much. If we set the target position to 0.05 times the original position, the movement will be a lot more subtle. We can also change the direction a bit based on the mouse X position. This is really starting to come together. But we still need one more component. In order to have realistic recoil, we need to be able to apply a force or a jolt to the weapon. In physics, this quick force is called an impulse. To add an impulse, we'll make a new custom block called Spring Impulse and give it inputs for X, Y, direction, and size. We'll change the X speed, Y speed, direction speed, and size speed variables by their corresponding inputs. Now we'll add a spring impulse block to the forever loop that controls the weapon. We can drop it in right below the sound effect block. For inputs, we can put in some random numbers. This will give the recoil more variety and let it feel less scripted. Let's try 10 to 20 for X, 4 to 10 for Y, -2 to 4 for direction, and 2 to 10 for size. This pushes the weapon to the right and slightly upward. Now we can test it. This is looking a lot better. Now that we have recoil, it should be pretty easy to add our final feature for this video, weapon sway. You may have noticed that the weapon stays still on the screen even when the player is running. To feel more dynamic and realistic, we should have the weapon sway around a bit with player movement. To do this, we can use sine functions. Here is a sine wave. The point in the middle can be represented by the equation y equals the sine of the time. We can use the sine function to move an object back and forth. We can also combine sine functions to make more complex shapes. For example, we can start with a vertical wave at x equals 5 times sine of 500 times time. Now let's add a horizontal wave at y equals -2 times cosine of 1000 times time. If we combine these two equations, we get a point that oscillates in the U shape. This shape will work well for our weapon sway, so let's add it to our script. After we have the equations, we can add them to the current target x and y values. Now let's test it. The effect definitely adds weight to the weapon and enhances the feeling that the player is running around, but it shouldn't be swaying all the time. After all, the player isn't jogging in place. Instead of constant swaying, it would be more realistic to have the sway depend on player speed, with more sway at higher speeds. To implement this, we first need to store the player's horizontal speed in a variable. Let's make a new variable for this and call it player horizontal speed for this sprite only. We can use the Pythagorean theorem on the player's x and z speeds to get this value. Since the player's speed variables are local to the camera sprite, we will have to use the value of sprite block from the sensing category. Now we can add this variable into the target x and y expressions. When we test it, we get much more realistic sway, with the sway stopping completely when the player stops moving. Now, there's still one last thing we need to fix here. Right now, the weapon keeps swaying even when the player is in the air. The player isn't jogging in mid-air, so the weapon should only sway when the player is on the ground. But how can we detect if the player is on the ground? Let's start by going into the camera sprite. We can start by making a new variable called playerGrounded for this sprite only. Inside the physics script, find the section that checks vertical collision. It starts with change camera Y by player Y speed and has an if block that checks if the space key is pressed. After the check for solid hitbox block, put a set variable block and select playerGrounded. Set the variable to 0 plus hitbox detected equals 1 and player Y speed is less than 0. This checks if there is a collision beneath the player. Using a math block like plus, make sure true is recorded as 1 and false is recorded as 0. It's important to recognize that this line of code gives the same result as an if-else block that sets the variable to 1 when the condition is true and 0 when it is false. Let's test this code. The variable should read 1 when the player is on the ground and 0 when the player is in the air. Now we can return to the Plasma Blaster sprite. Let's add an if-else block to the main forever loop. If playerGrounded equals 1, we'll run the normal swaying scripts. Otherwise, we'll run the springs with different values. First, we'll set the spring strength to 0.1 and the drag to 0.8. This will allow the weapon to swing more freely. Next, we'll take out the swaying for target X and Y and modify the target direction input. Finally, we'll set the target X, Y, and direction inputs based on the player's vertical speed. By adding these inputs, the weapon will swing slightly up and down when the player jumps. Now let's test it. That is looking so much better than the static weapon we started with. Thanks for watching. This video has opened up a whole new section of possibilities for future video topics. We could try different enemy damage methods, character spacing, pathfinding, and much more. We will definitely cover topics like moving platforms and camera tilting in later videos, and if there are any other topics you want covered in this series, be sure to let me know in the comments. If you enjoyed this video, please like and subscribe, and I hope to see you in the next one.